Welcome to The Explainer. Today we're taking a sleek, purely data-driven approach to one of the most infamous unsolved puzzles in American history, the Beale Ciphers. For nearly 200 years, this cryptographic mystery has totally frustrated treasure hunters and cryptographers alike. But instead of chasing old folklore and myths, we're going to look at a highly structured analytical framework that finally cracks the underlying mechanics of these texts. We're breaking down a brilliant, falsifiable model that literally turns historic legend into a testable geographic reality. Take a look at this sample of the original Beale Cipher data. It looks like pure random noise, right? Well, for decades, analysts have tried to decode all three of these texts using a single static key. Specifically, they tried matching these numbers to the word order of the Declaration of Independence. And sure, that traditional method worked perfectly for one of the texts, but it completely and consistently failed for the other two. It just left researchers with absolute gibberish. That is, until now. Okay, let's dive into this. We'll start with the Beale Cipher mystery, move on to the B2 calibration key, break down the mathematical shift, look at surveying the B1 location, and finish up with testing and falsification. Section 1, the Beale Cipher mystery. To solve a puzzle that's been broken for 2 centuries, you really need a completely new operational model. And that brings us to a groundbreaking framework developed by Triune Harmonic Dynamics, or THD. The research author, Kevin L. Brown, who is a researcher, inventor, and author, proposes what he calls the variable key survey hypothesis. Now, the core of Brown's hypothesis is incredibly smart. It states that the 3 Beale ciphers are not just independent, standalone puzzles. Instead, they are actually a linked operational ledger, where each cipher performs a very distinct role in a larger mechanical system. Let's quickly compare the old way of thinking with this new, stronger explanation. The old assumption was that you just apply a static key, again, the Declaration of Independence, to all 3 ciphers in the exact same way. But as we know, that only worked for cipher number 2, or B2. It collapses entirely for B1 and B3. Kevin L. Brown's model argues that B2 isn't just one solved cipher out of 3. Rather, B2 functions as a calibration layer. It's essentially the master key required to unlock the rest of the system. Section 2, the B2 calibration key. So if B2 is the calibration layer, how exactly does it work? Well, it acts as a mechanical master key. When you decode B2 using the standard method, it plainly lists the contents of the hidden vault. It tells us there are 2,907 pounds of gold and 5,100 pounds of silver. Now, for centuries, people just stopped reading there, completely blinded by the idea of all that gold and silver. But in a linked cryptographic system, this inventory isn't just an accounting of wealth. It is actually an embedded numeric register. It's data. The absolutely crucial detail here is the total sum. When you add the 2,907 pounds of gold and the 5,100 pounds of silver together, you get 8,007. This is the literal key needed to unlock the remaining ciphers. It's concrete, it's measurable, and most importantly, you can only find this number if you've successfully solved B2 first. It is pretty much the perfect built-in security measure. Section 3, the mathematical shift. Of course, having the master key is only half the battle, right? You have to know how to actually use it. Here is how the mechanics work, and don't worry, it's strictly 8th grade level math. Our base text, the Declaration of Independence, has approximately 1,322 usable words. Our shift value, our key from B2, is 8,007. Now, because 8,007 is way larger than the number of words in the text, you simply wrap it around cyclically. It's exactly like a clock going past 12. In math, this is called a modular reduction. When you divide 8,007 by 1,322, the remainder is exactly 75. That means our effective offset isn't thousands of words. It's a very precise cyclical shift of 75. So the crucial point is this. Instead of starting our decoding index at the very first word of the Declaration of Independence, like everyone has tried to do for decades, we now start indexing at word 75. In the standard text, word 75 is people. This single shift is the non-arbitrary correction that emerges directly from the internal logic of the cipher itself. Section 4, surveying the B1 location. So what happens when we take this new mathematically stable starting point and apply it to the previously unsolved B1 cipher? The results are completely transformative. When B1 is re-indexed using our 75-word shift, the random noise abruptly stabilizes. The text begins to produce highly specific, topographic language. It reads, 4 miles from Beaufort in the county of Bedford, near the excavated vault on the line of the ridge, at a depth of 6 feet, buried in iron pots with covers. Notice how the phrase structure here is strictly operational. And this brilliantly illustrates exactly why Kevin L. Brown's hypothesis is so powerful. B1 suddenly stops behaving like a romantic treasure myth, and it starts behaving exactly like a strict, surveyable field memorandum. It gives us a known historical origin point, Beaufort's Tavern. It provides a highly specific vector constraining the search to the line of the ridge rather than some massive, vague circular radius. And it gives us a vertical variable, a depth of exactly 6 feet. It is concise, functional, and materially specific. Just briefly, it's really worth noting that this exact same rule applies to the final text, B3. Under this shifted rule, B3 shouldn't be expected to produce beautiful prose. Instead, it logically resolves into a claimant's ledger, a structured list of names, beneficiaries, and identity markers. This perfectly matches the instructions found in B2, which stated the final document contained the names of the rightful owners. The whole system just locks together perfectly.
Section 5. Testing and falsification.
Now, a theory is just a theory unless it can be rigorously tested. Kevin L. Brown's model isn't some wild conspiracy. It is a falsifiable operational model. That means it lays out exactly how it can be proven wrong. For example, if someone finds that alternative, totally random numbers work better than the 8007 shift, well, then B2 loses its role as the key. If applying the shift to B1 doesn't consistently produce clear geographic language, the model falls apart. And physically, if a modern survey of that specific ridge reveals absolutely no anomaly, the physical model weakens. This is how real, data-driven analysis works. Conversely, the hypothesis gains massive credibility through repeatable confirmation. If independent researchers run the numbers and reproduce the exact same B1 survey fragment, linguistic stability is proven. If historical land records verify the Beaufort Ridge alignment, the context is validated. And most excitingly, if non-invasive ground surveys detect an anomaly at exactly 6 feet down along that ridge, the physical model becomes incredibly strong. Because this model is actually grounded in real-world data, we can outline a modern field test protocol. A surveyor today wouldn't need shovels and guesswork. They would first verify the math, applying that 75-word modular offset. Second, they would use historical mapping to construct a 4-mile ridgeline corridor radiating directly from the site of Beaufort's Tavern. And third, they would walk that specific corridor using non-invasive tech like ground-penetrating radar or magnetometry, specifically looking for dense metallic signatures buried at a depth of 6 feet. And this brings us right back to you. You don't have to take my word for it, and you certainly don't need to be a cryptographer from the 1800s to test this out. THD has provided a specific AI replication prompt. You can plug the data, the 8007 shift, and the modular reduction into an AI right now to independently evaluate whether B1 stabilizes into those exact geographic instructions. The tools to verify this are right at your fingertips. So will you run the prompt and see the variable key hypothesis for yourself? Thank you for joining me for this explainer. Keep asking questions and keep learning.